All right, so here's what we're up to. Here's our new toy. It's a high-speed digital video camera, and we're going to drop this ball bearing into the water and film the process at 600 frames per second, and we'll see what the splash looks like. To do this, we'll need to turn on extra light, because at 600 frames per second it takes a pretty bright light to make a good picture on the video detector.
Alright, what are we looking at? Well, we've turned the camera sideways, so air is to the left, water is to the right, and on the far right side we have a foam pad at the bottom of the fish tank to absorb the impact of the ball bearing. Now let's watch the splash. It comes down and beautifully goes in. Note the bubbles coming from air trapped in the cavities of the foam pad. Now let's watch it again more slowly. Note the vertical jet or spike that forms in the center of the splash. Beautiful. Okay, we'll do the experiment again, but this time we'll drop the ball from a much greater height. And now, instead of sort of slipping into the water and making a nice symmetric splash, the ball bearing will drill right into the water and form a tunnel of air right to the bottom of the tank. Much more energy, much more complicated.
Now we're going to replace the water by sand. We'll drop the same little ball bearing into the sand and watch the process of crater formation.
First, we'll look at the process from the side. The impactor falls from above, and here it comes. Bang! And look how a curtain of material ejected from the crater flies out in all directions, leaving behind a cone-shaped crater with a raised rim. Let's look at that again. But this time we'll do it a little more slowly and a little more closely. Here comes the impactor. There's the impact. We actually do a lab in our astronomy courses studying how the diameter of the crater is related to the mass and speed of the impacting object. Now let's look at it from above. The object drops from just above the camera, and you can see the beautiful symmetric pattern of ejecta and the formation of the crater in the sand surface. And once again, we can do that again. We can slow it down a little bit, and we can zoom in and see the process once more. Very nice. For our final test of our high-speed video camera, we want to look at a classroom demonstration that we sometimes use to illustrate the idea of a chain reaction, like you might see in nuclear fission. Nuclei are too small to see conveniently in the classroom, so we have a kind of mechanical analog of it. What we have is an array of mousetraps. There are 65 mousetraps in our apparatus, and they're all set ready to snap, and we put ping pong balls on top of each of the mousetraps. Now, the mousetraps could represent the fissionable nuclei in a sample of uranium or plutonium, and the ping pong balls could represent the neutrons in those nuclei. Neutrons can induce fission in nuclei by collision, and they're also released during fission. And we put the whole apparatus in a plexiglass box and drop one single ping pong ball into the middle. Let's watch. We're filming at 300 frames per second. We drop the single ping pong ball into the middle of the system, and at first only about 2 others are launched, but then catastrophe. And in fact, 62 of the 65 mousetraps are triggered in the process. And if we take a look at the aftermath of our simulated nuclear explosion, we can see ping pong balls all over the place.
Aftermath.
Almost all, 95% of the mousetraps triggered. A chain reaction.
Okay. Come around over here.